Hi, I'm Steve Pieper, and I'm here to talk to you about high-resolution neuroimage visualization along with 3D Slicer and CloudXR. These are some really interesting technologies, and we're going to give them a shot and see how they work well in practice. So I think the problem we're really trying to address here is that traditional interactive graphics of all kinds, but in particular VR, required complex equipment for all kinds of practical reasons. You needed to get fast reaction from the user, you needed to get that input into the computer, you needed to render a result, and you needed to get the images back on the display. And while this has certainly been possible and it's getting easier all the time, there is this question of how to leverage the biggest, most impressive computing and work on the hardest complicated applications with the simplest user requirements. And so what we decided to do was to really explore this using an experiment that pulls into play Amazon AWS EC2, a software package called 3D Slicer with an extension for Slicer virtual reality, and an NVIDIA CloudXR technology that's recently become available. And we're going to apply it to a very large neuroimaging data set and see how well everything performs. So first, I want to give you some background about the 3D Slicer application and the 3D Slicer virtual reality extension. So 3D Slicer itself is an open source medical imaging application. It's been available for many, many years. It's now coming close to release of version 5. It's got quite a long history of edits and refinement, so it's a pretty sophisticated application by now. It's been downloaded all over the world almost 1 million times, very active forum, lots of people doing research and contribution and development, and it's been supported by the NIH and other funding agencies for quite some time. And basically, internally, what it is a C++ application with an embedded Python interpreter, and you can extend it in either one of those languages. It's written with the Qt user interface environment, with the visualization toolkit VTK, makes extensive use of ITK, the Insight toolkit, and of course, it's all built on standard computing platforms and graphics libraries such as OpenGL. It's a very modular platform. There's a core data model that handles all the real-time interaction, and then there's a separated logic category for code that manipulates that environment, and then there's the user interface layered on top of that. Internally, the data is stored in what we call the medical reality markup language scene, or MRML scene, and it can be saved and restored in XML or as a medical reality bundle as the document format encapsulating all of the visualization settings and data model. It's pretty extensible in terms of supporting the common medical imaging formats. DICOM is the clinical standard, and then there are many, many other research formats. But Slicer, importantly, can handle segmentation, interactive annotation, linear and nonlinear transforms, registration between data sets, and then also time series data sets. And all of these can be visualized, quantified, shared, and operated on. We do a lot. In fact, the driving application is clinical research, and that means Slicer is often used in ORs together with real-time imaging equipment, therapy guidance. The internal structures of Slicer are all set up to be real-time and allow various kinds of analysis and display. And really that's driven, again, by what clinicians really need for improving the state of the art in their work. The way we organize things is in terms of a system called extensions. There are specialized apps that can extend the Slicer ecosystem, and they're built around specialties, for example, prostate urology applications or radiotherapy. They can be in either C++ or Python, and they're built nightly and made available on top of the current release and the current nightly build of Slicer for Windows, Mac, Linux. We take care of that as long as it's open source. So everything we provide is open source. And that's very useful because it's easy one-click download for people, but we also have the option for people to build their own custom applications, completely leveraging all the build systems and all the work that's available in core Slicer, all that stuff about medical image management, but then to extend that with their own custom code, with their own user interface that may look nothing like the 3D slicer, may hide a lot of the functionality. And we encourage people to do that because it helps build our community of skilled developers, but it also helps get the technology into real use among people who are able to treat real patients, because unless something becomes a medical device, it really is restricted to just research mode. At this point, there are quite a few people around the world who are expert, really, slicer developers and who are able to do this customization and extend. And I'll give you some examples of work done by some of these colleagues. Isomics, my company, has been around for the longest, probably, in slicer development. Kitware has been around for a very long time as well, and does other notable software packages like BTK and ITK. Ibatinka and Pixel Medical are relatively new in the field, but are also highly skilled at doing this kind of development. And we think actually probably, and we know of companies that have internal expertise, some of it just proprietary, that they don't necessarily even have to interact with the community. This is all enabled because Slicer's license is very permissive. It allows commercialization, and it's not a viral GPL license, and we keep all that GPL type stuff out of our Slicer code base. So one of the things that's been enabled is a virtual reality infrastructure. So here's Csaba Pinter using the Slicer virtual reality infrastructure, and he uses controllers in this case to control views of a spine and an imaging plane through a spine and some simulated screws for implantation in the spine. Everything that's available in this 3D slicer view is also in the VR environment through OpenVR and the BTK OpenVR wrappers. So there's quite a bit of functionality that's just leveraged from other slicer use cases and made available in VR. Here's an example of a very important use case in cardiology. This is the Slicer Heart team that comes out of Matt Jolly's lab at the Children's Hospital of Philadelphia, CHOP. And what you see here is, this case, it's a CT scan of a patient. They're looking very, visualizing the inside of the lungs there. You can also see the heart behind it. This is a very good example of a high quality clinical CT scan. It's easily able to be rendered in real time on current systems. It's used pretty routinely now, and routinely under research controls for pediatric heart surgery. So for visualizing congenital heart defects before surgery, or for the implantation of devices. Here's another example of a clinical use case. This one not yet available clinically, but in prototype form. It's a collaborative environment where you can visualize patient data, multiple people using the same 3D slicer instance at the same time, communicating in terms of gesture and real-time communication, in this case to experiment with different pathways for inserting doing a brain biopsy. This has been funded by the EU and this Spanish government. It's been implemented by Ibatinka, which is a company in Las Palmas de Gran Canaria in Spain. And they're a slicer developer group, a good example of a group that can do really amazing things with the platform. So that's 3D slicer as it exists today. And most of that is the traditional, you plug a wire into a monitor and you render with a video cable, the video card. And what I want to talk about now is some of our experiments in cloud rendering and use of cloud computing. So for the first example I want to talk about is a very large data set and some work that I did a couple years ago to experiment with cloud rendering. So this is a remote desktop application running on an AWS EC2 instance, a virtual machine that had an NVIDIA A100 card on it. And this data set is of a human brain. It's an ex vivo human brain that has been imaged at high field strength with a magnetic resonance scanner that's 7 Tesla, which is the highest commonly available field strength right now. This took several days to scan. It's a full brain data set, 1760 by 1760 by 1280 in float, which means it's about 15 gigabytes. This particular rendering that you see here is very, very impressive to me and to other people who are interested in neuroanatomy. It was implemented using the cloud consoles and the X11 desktop with the X11 VNC remote desktop server and a no VNC client, which is very handy because it means that you can see your VNC session in a web browser. But implementing something like this obviously takes some amount of cloud expertise. So it's really not something, it's ready to use for anyone, but maybe not technically accessible to a lot of users because it's command line driven and a few other details to set up to get your drivers in place and whatnot. But that use case has been very motivating. And AWS actually has taken the same concept and made available what they call app streaming, which incorporates a remote desktop and a web service front end, allowing you to send someone a link that is to a desktop application running on one of their cloud instances. And this has really kind of revolutionized some of the remote training that we do on these high performance computing applications, because we held a workshop just the other day with about 80 participants who all wanted to learn how to use a deep learning environment with GPU-based backends that was for medical image segmentation, so 3D segmentation of complex medical image volumes. And the team at AWS was able to work with us to set up an image that we were able to instantiate a GPU-backed machine, one for each of 80 people, ramped it up within a minute of starting the workshop, and then people could use it, a uniform environment, access from whatever machine they had, and then it was shut down at the end. And very, very efficient, cost-effective way to run a workshop with serious computing hardware. So the app streaming is a very, very powerful thing. But it hasn't really been, app streaming natively doesn't necessarily support the VR applications, because obviously you need to connect a headset to it somehow. But NVIDIA has come up with a solution they call CloudXR, which is a service, or it's a client server software development kit that you can split the client and server in such a way that all of the heavy duty computing and graphics rendering is done on a remote machine. I mean, it could be any machine, it's just connected over the network, could be a local network or the internet, but one of the places you can run those servers is in a cloud provider. So AWS, for example, offers images and easy to boot machines, which bring up a service that you can then have CloudXR running in. And on the client, you need a CloudXR client, but it's available for any of the current standard, most of, let's say, of the current standard mainstream VR headsets. So the Oculus Quest is a common one these days, but other ones, Windows Mixed Reality, some of the HoloLens, I believe, and some of the other AR, VR infrastructure. So the nice thing from my point of view is that it just works with the Slicer executables, with the SlicerVR, everything that we looked at. There's no modification of the binaries needed, just runs on a system with this installed. So here's the result. We worked on this for a few weeks and found a way to implement a remote rendered VR session. This is recorded off the headset running in my office, and it's accessing a GPU that's running somewhere in AWS. It's, like I say, an unmodified version of the 3D Slicer application with SlicerVR. You can see this is a very large data set. We're looking now into the brain. We're able to look around, do some clipping and cropping and see some of the structures. I think one of the things that really impressed me about looking at it this way is that you see the blood vessels in the brain look like tubes. And when you have the brain about this size in front of you, one of those blood vessels looks sort of like an aquarium tubing. It's clearly a tube. It's not just a bright line. And here you can see, looking into the ventricles, quite a bit of detail. That's very, very nice detail about the internal structure of the brain. So this was done on what's called a G5-4X large. It's a 24 gigabyte GPU with a A10G NVIDIA card in it. The going rate right now from AWS is $1.64 an hour, and this is just turn it on for an hour, turn it off, and that's what they'll bill you. It runs on the client side with an Oculus Quest 2, which is only $299 system, and is pretty nice actually. And it's cable modem and just regular Wi-Fi, so nothing too dramatic. But I think the results were pretty good. I would say there are some considerations to keep in mind. The original data set was in floating point, 32-bit floating point, and that was just a little too big for that graphics card. So we cut it down to short, to 16-bit short integer, and that allowed a lot of things to work a lot better. Obviously, there's some things to figure out about the VR environment. We did have to downsample or turn down the resolution a little bit on the rendering to get better frame rate. That may have been because of the either the graphics card with this size data or the video encoding. But in any case, it still looks really, really sharp, but not as sharp maybe as it could be. And everyone, you know, when interacting with this, there are times when things would take a while to render, and there would be a little bit of lag, maybe you noticed in that video, but also there's some compression artifacts visible. It's not as sharp as looking at a monitor with the same thing rendered. And you can sort of understand that because when you're looking at it in VR, every frame is new. Every time you move your head, it's giving you a new, fresh frame. Whereas when you're looking on the traditional, say, mouse-based rotation, you stop and any compression artifacts get washed away when the full res data shows up. So it's getting there. And of course, we have a lot to do in terms of the controls and mapping them for better visualization. But I'd say it's close. So let me wrap up here and say that I want to thank all the partners who helped make this possible. Obviously, you've seen work from a number of different places: Eva Tinka, Kitware, Children's Hospital of Philadelphia, the PERC Lab at Queen's University in Ontario has been a great help. At Mass General Brigham, we're supported by the NIH, so big thanks to NIH funding, both major funding from the Neuroimage Analysis Center at P41 at Brigham and Women's Hospital that I'm part of. Also, big thanks to the AWS team. The computing group there helped a lot, and NVIDIA folks helped troubleshoot some of the issues that we were running into. So it's been really, really helpful collaboration. I would say in summary and takeaways from this work is that sort of unexpectedly, the current generation of cheap VR headsets is actually pretty good. It's getting better very, very quickly. I can sort of imagine a day when I might prefer to wear one for high resolution visualization compared to a monitor. I'm not really there yet because you'd have to wear a headset all day long. But when you need it, it's already pretty good. And I suspect they will continue to get better very quickly. The interactive controllers are already very nice for working on this data. I think also we're in a number of research projects working with very, very large data sets. So this brain is a good example one, and it's public domain, so it's a good driver to explore with. But other applications, other fields, micro CT, high resolution microscopy, there are a number of places where huge data is becoming the norm. And there is a kind of a crisis in the field of matching the visualization tools to the size of the data. And so being able to do high performance GPU based rendering where the data already is potentially revolutionizing the ability to make use of all this data. And I should say too that the ability to match that with the on-demand computing, again, traditionally when you needed to have all the boxes and all the cards and all the computing in your office with you or in a room nearby and run cables, that severely limits how quickly you can experiment and change things. When everything is set up in an on-demand environment, you can get an app streaming instance or a cluster of EC2 instances. That's a much more convenient way to experiment and then actually optimize your use of the resources when you're actually actively doing the visualization or analysis. I guess one of the things that shouldn't have surprised us, because we know people play video games all the time online, but the network latencies were not as big practical problem in this. I think if you were looking at fairly simple content rendered remotely, you would have a hard time recognizing the difference between a machine that was in the same room with you versus a machine that's hundreds of miles away. And that won't change, I don't think, except maybe it'll get a little faster as networks continue to improve. What we do notice, though, is that there will always be a need for more GPU memory and faster rendering, because these data sets are getting bigger. And I think along with that, we will see improvements in the video encoding so that we don't see any artifacts while rendering. I think these are probably going to get resolved because there's only so much resolution the human eye can pick up, and only so fast we can move our controllers. But we need to match that then with the GPU performance, which has always got to grow to match the to try and keep up with the amount of data that's being created. So with that, I'm going to say thank you, and I appreciate your time, and look forward to hearing from anybody who's interested in pursuing these technologies. You can either reach out to me or any of the other people I mentioned, and we'll be glad to help.